Hello, my name is Jacques Gautier. I am a member of the Lastic Laboratory of the French National Geographic Institute, and I will present you our work about the co-visualization of air temperature and urban data for visual exploration. The context of our work is the analysis of urban heat island, a phenomena which causes higher temperature in urban areas than in rural areas. Climate and meteorological scientists are able to simulate temperature data at city scales. This simulation becoming more and more precise, they expect to visualize this simulated data at a city block scale in order to improve the study of urban heat islands in the context of the European project IEEEVIS. Climate visualization often propose to represent global trends in the temperature evolution at a global scale. Other works propose to represent the temperature evolution inside the city in 2D or in 3D by, for example, representing the temperature projected on the ground or on the building of a urban 3D model, or by representing the temperature related to a building on the surface of its building in a urban 3D model. Other works coming from the scientific visualization domain propose representations showing the temperature evolution in the 3 dimensions of space. However, all these different representations lack interactivity to perform a real exploration of both urban and temperature data in order to provide a visual analysis of a relationship between climate and urban morphology. Co-visualizing temperature and urban data, meaning enabling the cross-visual analysis of both these data in an interactive graphic representation, is difficult because it implies to combine heterogeneous data. For our case, we dispose of simulated air temperature data, which can be represented as a 3D irregular grid with a horizontal resolution of 650 meters and a vertical resolution between 1 meter near the ground and nearly 20 meters near the building roof. We also dispose of urban data composed of a 3D urban model with a metric resolution, allowing to explore the city at a fine resolution and identify morphological structures, and of morphological indicators with a resolution at city block scale. We focus our work on these two issues: how to visualize simulated air temperature data at a city block scale, and how to visually explore both these data along the 3 dimensions of space. We propose to represent simulated air temperature data projected on proxy geometries based on the geometry of the grid's 3D cell. To enable data exploration with different viewpoints and to fit to some expected task, we propose 3 different proxy geometry. We propose to represent data through stacks of horizontal planes, which could be used for analyzing the horizontal distribution of temperature, through stacks of 3D point clouds, which could be used for analyzing the 3D distribution of temperature, and through stacks of road-based vertical planes, which could be used for analyzing the vertical distribution of temperature. For all these proxy geometries, temperature value is represented by a color scale. To improve data exploration, we offer the possibility to modify different graphic parameters, such as the transparency of the planes to reduce visual occlusion, or the density, the size, and the position of the points in our point clouds representation in order to improve the visualization of each level of data. We also propose to modify the style of the urban 3D model by, for example, hiding or applying transparency to the building facades, or by using the building colors to represent a morphological indicator, such as the local climate zone classification. We propose different kinds of interactions in order to perform a visual analysis of the simulated air temperature distribution. By, for example, modifying the color scale used to represent the temperature value through an interactive histogram of the temperature distribution in order to highlight specific range of temperature value. Here, by reducing the temperature range represented by the color scale, we are able to highlight the temperature differences located at the center of the 3D scene. But we also propose other interactions, like an unlimited filtering of the temperature values in order to identify spatial gradients in the temperature distribution. Here, we can first see the location of the highest temperature values, represented in red, near the ground surface. Then, the location of the lower temperature values at different heights above the ground. And finally, the location of the lowest temperature values, represented in blue, near the building's roofs and at the end of the 3D scene. And so we can identify here two spatial gradients, one vertical and one horizontal to the bottom of the screen in the temperature distribution. The user can navigate into the 3D scene with zoom and pan function and by modifying the camera orientation. This navigation, added with the possibility to change graphic parameters, such as the color scale or the proxy geometry used to represent the data, allow our framework to providing a visual analysis of both simulated air temperature and urban data in order to analyze the relationship between temperature and urban morphology. This framework is implemented as a web application using Three.js and OpenGL. We submitted our framework to meteorological experts. It gives us relevant feedbacks to improve geometric proxies and interaction functionalities, but this evaluation has to be conducted with more specialists and in a more controlled way. The horizontal plane were appreciated even if they find the transparency not so efficient to visualize several levels of data. The use of 3D point clouds was controversial to visualize the data distribution along the 3 dimensions of space. However, the vertical planes were really appreciated for both horizontal and vertical distribution analysis. They find the animated filtering not so efficient to identify spatial gradients. However, they really appreciated the use of the interactive histogram to modify the represented range of temperatures. To conclude, we elaborated and implemented an operational framework for the co-visualization of simulated air temperature and urban data. We are waiting for more precise simulated data, and we could also visualize additional data such as the building energy losses and visualize the temperature components of climate data. To improve the visual analysis capacities of our framework, we could integrate our contribution into an immersive visualization system. So I thank you for your attention, and I'm waiting for your questions.